Hello, and welcome to this lecture on finding a battery cell's usable capacity. In this video, we're going to go through a Python tutorial and how you can calculate a battery's capacity or the amp-hour throughput during a charge-discharge cycle. This process of approximating capacity is known as Coulomb counting. So with that introduction, let's go ahead and ask some background questions and go ahead and dive into it. So, have you ever had a phone go from 20% charge to empty in just a matter of minutes? You're using it and all of a sudden, bam, it's dead. Well, what about a laptop that started to die on you when you're in the middle of an exam or a job interview, or maybe you're playing a video game, right? And you get that pop-up that says, plug in now or it's going to go to sleep. These issues are directly related to the power and capacity of the batteries that our equipment uses. The capacity of a battery is the amount of energy that it can store. And when a battery is made, it starts with a very specific energy storage capacity. Over time, however, as it gets older, some imperfections and degradations occur, and so the battery's capacity is less than, when it was brand new. Now, this degradation in capacity or reduction can be caused by a myriad of factors. This includes undesirable chemical reactions, or by overcharging the battery in ranges where it really should not be operating. For example, when we overcharge a battery, it can cause lithium deposition at a negative electrode surface. And when this happens, lithium transitions from liquid phase solution to solid phase. And effectively, this becomes a resistor that inhibits the battery's ability to efficiently charge and discharge the cell. Now, you might be wondering, obviously it's important for your laptop to have battery capacity lasting a certain amount over time, but why else might monitoring battery capacity be important? Well, how quickly the capacity fades can really help us understand if a battery should be used in a specific application. If you think about phones, that have a shelf life generally of 1 to 2 years before people switch them out, emergency power sources that you don't use often, but when you do, you really need to make sure that it's working. And electric drills, the battery capacities on these are all very different, and the expected lifespan is highly variable as well. So what manufacturers can do is they can monitor the capacity of a battery once they've built it to see if the initial battery quality is meeting desired tolerances for production. So comparing maybe a batch of 100 different electric drills and making sure that the capacity is all within a certain specification. In addition to that, since battery capacity will change over time and degradation mechanisms are highly variable, it's important to look at, let's say, the end of your warranty period for your electric drill, making sure that the battery capacity is sufficient at that end of the spectrum as well. So monitoring capacity from the very beginning of a battery's development and production all the way to its end use is important so that we can assess for potential defects in the battery. Now, there's many ways that we can approximate battery capacity, but a common method, and the one we're going to highlight in this video, is Coulomb counting. So Coulomb counting is a mathematical way where we're literally just counting the coulombs, the energy throughput that is passed through the battery. And the way that we do this is by integrating the current with respect to time. And I'll show that in the equation below. So pretty simple. We have our energy throughput, Q, and as we multiply our current that's been applied relative to the time difference or time duration of that specific current. So if you can imagine, we've got a battery, maybe it's a 2.5 to 4.2 volt cell that is a 3.5 amp hour or 1.5 amp hour, then this time differential will integrate it and calculate the energy throughput. And if we were starting the battery at its minimum operating condition, where it's around 0% state of charge, and ran it all the way with a supplied current until it hit its maximum voltage operating condition, or 100% state of charge, and we continue to apply some supplemental current, maybe tapering it to make sure that we are maintaining a voltage. So, that can get us to our approximate 100% state of charge. So that's why Coulomb counting can be highly useful. It's relatively efficient, easy way to approximate the capacity. It's not technically the true capacity of the cell, and we'll talk about that at the end of this lecture. But it's pretty important. So now that you know that, it's nice to know that the math is useful and there, but how do we do this in a live test? Well, to measure the battery's capacity by Coulomb counting, we want to bring the battery's state of charge down to its nominal zero state. And then we apply the current until we've reached the battery's nominal full state of charge. We repeat this process going from nominal full to nominal zero, and then reverting from zero to full. And this process allows us to capture the charge and discharge throughputs, and then by analyzing the difference between those two, we can look at the coulombic efficiency of the battery. In other words, how much stored energy can we use relative to what we're putting into it. Now, I mentioned nominal full state of charge, nominal 0 point. The reason for this nuance is that at these conditions, we're really not at the true full charge or full discharge scenario of a battery. If you look at your phone, for example, let it die on you, go down to 0%, and then wait 5 minutes and try to hit the power button. You'll probably see a light flicker on. Clearly, there's some energy still there and some potential. It's just an amount that we are not able to access usefully. And generally, that's because there are safety limits or suggested operating limits that have been placed on the battery or the product that uses it so that your battery's life is maximized or that it maintains a certain standard of performance during usage. So that's by design, it's by intent, but just know when you see 0% or 100%, it's probably not the true 0 or 100% that theoretically we could actually get out of the battery. So that's true for phones, for laptops. Pick any electric lithium-ion battery-powered source, and that's generally true for it. And again, these ranges make sure that your battery is operating sufficiently. Enough though about Coulomb counting and backgrounds on capacity. Let's dive into an example with some public data for cycling from NASA. So I pulled this off of Kaggle, and we're going to get started by first importing our boilerplate. So I'm going to import pandas, NumPy, and then matplotlib, our basic plotting library. We'll load our data set. Now I've downloaded that locally, so I'm going to specify my path. And then we're going to read our unique charge and discharge files. What's kind of cool about this data set that NASA provided is that each file is separated based on charge, discharge, or impedance measurements. So with that, we can see a pretty quick difference between charge and discharge profiles. So I'm just going to explicitly state the charge and discharge profiles here in different data frames. You're going to notice programmatically, it's not super efficient, and that's fine. The purpose here is just to highlight some of the differences that we'll see in the test data. So you can see here I've loaded my data frames. I've extracted out the current, voltage, and time to lists. And then we're going to go ahead and plot the data. And I want to look at both the charge versus time, the voltage versus time for charge scenario and for discharge scenario. So let's go ahead and do that. And we're going to add a legend, and we're going to see what that looks like. Okay, so notice here at the beginning some interesting things. So first, obviously the time has not been rescaled. This isn't total test time because they're both starting at a 0 condition. But what you can see from the beginning of the test is this is going from, for discharge, around 4.2 volts down to 2.5, and then charge from 2.5-ish to 4.2. You notice also that the test time is a little different between charge and discharge. And what this probably tells us is they're tapering the voltage, or tapering the current during the charge scenario. So as they get up to a full charge condition, they're going to back off the current a little bit to make sure that we can charge the battery just a little bit more. And we can see that if we go ahead and plot the current profile. So let's do that. So I'm going to go in, and we'll just do plt.plot, and we're going to do time charge along with current charge. And if I just look at that, let's just do, and we'll give it a quick label, plt.xlabel. That's our time in seconds. And then let's add our y label, and that's going to be our current in amps. So just a quick example. We look at this, we should be able to see a curve going downwards once we hit around, what is this, about 2,000 seconds. And before then, we should have just a flat line current that's being applied. So I'll go ahead and rerun this cell. We'll let the next plot, and you'll see that's exactly what happens. So when we look at current versus time for charge, we have a specific current applied constantly. And then as we hit our 4.2 volts, immediately there we're going to start tapering down so that we can apply less current, get a little more energy into the battery, but maintaining that 4.2 voltage. Now that we've looked at one example data set, the voltage profile, let's go through and actually calculate the capacity and energy throughput using Coulomb counting. So I'm going to go through, and again, this is just a simple example, so we're not going through the most efficient programmatic methods here. We're just going to go through a way that perhaps you might be able to do this as a new battery engineer or Python user. So I'm going to start by declaring a list. I'm going to make an empty list, and we're going to set an initial 0 condition for our throughput for charge or discharge. Then, since we already have our voltage charge list from above, I'm going to iterate through that. So for I in range of the length of the voltage charge list, we're going to first, we're going to calculate the energy that's passed through. And again, that's the because that's an integral, it's the current of an individual point in time multiplied by the time difference. We have to look at time, I times I minus 1, or in this case, I plus 1 minus I. To do that, obviously, we have to, we're going to lose one of the data points. So we're going to have an if condition. If I is less than the length of the voltage list, minus 1, because Python is 0 based, then we're going to calculate the energy charge for that state, or that point in time. Then we're going to append that to our energy charge list, and that's just because it's nice to look at the entire charge and how that's going through versus time, because the energy charge is not going to be constant, as you see in the charge plot above. That's going to be tapered at some points. It should be relatively constant in this region here, but it's going to taper after about 2,000 seconds. So then, for our throughput charge, we're just going to set that equal to the prior value plus the energy charge calculated at that instant in time. So I'm going to do this and complete it for discharge as well, so the exact same process. And then we should be able to look at our throughput charge and throughput discharge. So let's go ahead and run this cell. And what you'll see, so for charge, it shouldn't be too surprising here. You're able to put more energy in than you get out. That's just life, there's imperfections. So about a 1.5 amp hour battery, and the amount that we're able to use relative to what we put in is pretty darn high. And we can calculate that just by doing a quick, dividing our throughput discharge divided by our throughput charge. And if we calculate that, this is known as Coulombic efficiency, and our Coulombic efficiency is more than 99% for this scenario. That's pretty awesome. So now that we've done that, let's look at a more detailed example. So this again was a NASA battery data set. We looked at one snapshot, Coulomb counting for charge and discharge for, let's say it's probably the beginning of that battery's life. Maybe it's somewhere in the middle, but we looked at one snapshot. Now, let's look at the entire test profile for the battery, at least for all the cycling data that they have. So I'm going to go first and look at the metadata for this Kaggle data set, and we're going to read it and just see what shows up. Okay, so a couple high-level things that we can see here. So for all the data files that are there, and there's about, I want to say around 12,000 or 1,200 of them, you'll see that there are three main types of profiles. We have charge, discharge, and impedance data sets. They also provide the start and stop time for the test profiles and unique battery IDs, so we can see which files correlate to which specific batteries and the temperature that these batteries were tested at. We also have the file name that we can filter off of, and then they provide the capacity of the battery. So that's interesting. There might be some differences in some of the batteries that were tested. So with that, we want to look at the capacity across the life for one battery. And just to speed things up here, I'm just going to look at the first battery. So we're going to filter based off that initial battery ID, which is B0047. And so I'm going to declare that looking at our meta data frame. And then I also only want to look at charge and discharge test profiles. So let's exclude impedance tests from here. Obviously that does influence the battery's life, but we just want to look at cycling so that we can do a direct measurement on the capacity from cycle charge to the next cycle charge discharge. Now with that, we're going to filter our metadata. So we just want to look at how many test profiles we have where the battery ID is the same as our very first profile. And with that, how many charge discharge profiles we have. So I'm going to do that in this line here, and then I'm going to make a list of all the files that are associated. And I'm going to do that so that we can iteratively read each file, and we'll run a function so that you can calculate the energy throughput. So let's go ahead and run this cell, and I want to just put out the df meta now that we've cleaned it to just show the very first battery and its test profiles. So if I look at that, you're going to see we've got 144 data sets specific to battery B0047 for charge and discharge profiles. So this is kind of cool. You can also notice now they already have the metadata in the header, right? You can see the capacity going from 1.6 to 1.5 and so on. But we can calculate that for ourselves if we didn't have this metadata set. So now that we've isolated the file names that we're interested in, let's go ahead and read in all the data, and we're going to set them to a data frame. This is going to be handy so that we can iteratively calculate the throughput and capacity performance at each cycle. So one thing that I'm going to do, if you have the file download locally to your path, it's going to be helpful to import OS and then specify the path where your data is being held at. Once we do that, we're going to declare an empty data frame. And you don't have to do this. I like concatenating it all to a master data frame, but it's certainly not necessary for this. That's just if we want to just take everything, look at it in one full sweep. What we're going to calculate on is we're going to make a list of all the data frames. And the way that we can do this is by using OS along with pandas. So we're going to read each CSV file based on the path that we've specified. And then we're going to do that for each file in our file list. So if you recall from above, we made our list of files based on the list of files that were specified here in this file name column. Okay, so let's just go ahead and run that. And if I look at df list, we should see multiple entries. And this is going to take a couple seconds to run. And as we see on the output, right, we have lots of different entries for different test profiles. And if I look at df master, that should also show us one large data frame with a whole lot of data. In this case, it looks like 125,000 rows. Okay, great. So we've got our list of data frames. So now if we want to calculate the throughput capacity, there's a lot more efficient ways than just doing an iterative for I in range looping process. And so we can certainly do that. For here, what I'd just do is, let's just throw this in a function. We're not dealing with gigabytes of battery test data. We're really looking at maybe a couple 100 megabytes at most here. And so this is pretty simple. So the speed impact is going to be marginal here, but there are certainly more efficient ways we can do this. So I just copied and pasted our code from before, and we're going to throw it into a function. So, take out the charge or discharge appendages, because we're going to apply this to both charge and discharge profiles. For this function, we're going to have data frame as our input, and then we're going to extract the voltage, current, time, and then calculate that energy throughput. And we're going to return that throughput from our function. Now, what's important is making sure when we call this function, we want to retain the throughput for every single profile, for each charge and each discharge. That way, we can look at the capacity and the differences in the usable capacity, right, the discharge side over time versus the charge. You might see some unique differences from time to time, so that's important to clarify. And if you wanted to calculate the Coulombic efficiency, you would need both of these energy throughputs. So let's go ahead and run this. As you can see at the bottom, I'll be calling this throughput function, making it into a throughput list for each data frame in our data frame list that we created in the lines above. So now that we've done this, it's going to print out tons of lines, and you'll see it's oscillating, right, back and forth, positive, negative. So this is good. This is our charge discharge. Now, to be clear, this is just unique to the NASA data set where it's purely cycling, and we're lucky that when we exclude the spectroscopy or the impedance testing, that we don't have any uneven or non-oscillatory from charge discharge, right? On occasion, these data files could be broken up such that you have two charges, right, going from 0 to 50% and 50 to 100 or something like that. But here we see a pretty nice alternating profile, and we see the capacity, changing over time. So let's go ahead and plot this, though. Obviously, reading such a list is not super helpful. So the first thing I'm going to do is split this data set, this throughput list, into charge and discharge profiles. And I'm going to do that, if we notice at the very beginning, our discharge as the very first profile. So we're going to take that and have it oscillate between every other profile in our throughput list. And then our charge list we're going to make based off of obviously the second iteration. So at our first index, and then iterate every other one. Now, in addition to looking at the charge discharge throughput, let's go ahead and add a cycle count to our list. It'd be important to look at how this capacity is changing, or how our throughput is changing between, let's say, our first cycle and the last cycle. So the way I'm going to do that is assuming that these lists are the same length, then I can just declare a list here, I for I in range length of the discharge throughput, give me my cycle list. And let's do a quick test. Let's print this to make sure that the charge and discharge throughputs are the same length. Okay, great, they are. So that's a pretty good check, and we expected that. So now we're going to just change the sign to discharge throughput. It's oscillating, but obviously that's just a sign notation based on if you're putting energy in versus taking energy out. So I'm just going to make them all to the same absolute basis, and we'll do that by putting negative value for value in the discharge throughput list. Finally, let's go ahead and plot this, and we'll consider both charge and discharge here. And let's just see what we can infer. Okay, so take a minute to digest this. A couple things that should be immediately apparent. We have some outliers here that are kind of interesting. Now, if we go back to the metadata, we could probably explore and see if there's more information to glean. Obviously, seeing a jolt in capacity or in throughput from 0.8 amp hours to almost double that, 1.4-ish, that's not necessarily indicative that the battery capacity is really there. More than likely a test ran that was just partial charge. Maybe it went from 50% state of charge to 100, or from 0 to 50. So, One thing, though, that we should be able to notice is if we look at the initial discharge capacity, at the very beginning it's around 1.6, 1.7 amp hours, and then it's steadily declining across the profile. So as we go from our first cycle to our 70th cycle, there is a clear trend that the capacity of the battery is declining as the battery is aging, and it's no longer becoming as useful as it used to be at the beginning. So this is kind of cool here. We could probably, if we wanted to, look at how much this capacity has died relative to the beginning. So if we want to look at the initial capacity. So this is kind of ad hoc, so let's just go through and do that. So if we have our discharge throughput, so I'm going to just write some code and we'll say, capacity retention. And that's going to be equal to a list, and we're going to have, let's just do this in a for loop. It'll make it easy. Try and range length of our discharge throughput list. We are going to calculate the capacity retention. So capacity retention is equal to, and it's going to be our current one divided by the initial discharge throughput. And then let's append that to a capacity retention list. And then we should be able to see our results. Now to run this, there are two things we need to do. First, we need to specify what that list is. So we need to make our empty capacity retention list. And then also we indented, looks like once too much. Let's go ahead and set that back. So now we should be able to have our capacity retention. And let's run that. So we can see, and this is normalized obviously to the initial. So we're starting from full capacity down to what looks like 70%. And that's pretty quick, 70 cycles. Certainly when you're using your phone, I charge mine every day. It probably goes to full discharge every 2 days or so. So in 1 year, you're going from full capacity in this particular battery that NASA was testing down to 70%. And let's, if we plot that, you should see the same profile here, right? It's just steadily declining. So on our final note, we've used Coulomb counting to approximate battery capacity, but it's important to note how capacity, really the definition of it can vary. For example, if we recall that SOC 0% and 100%, the state of charge, are generally defined by manufacturers, it's not the true dead or the true full charge for the battery. Some individuals will also define capacity as the amount of usable stored energy in the battery, measured during a battery discharge. Others might define the capacity as the energy that you can put into a battery, measured during battery charging. However, these definitions fundamentally ignore that there's extra capacity available outside of the battery operating window that manufacturers recommend. When we define capacity instead as the total amount of energy stored in a battery, whether it's usable or not during operations, we can capture a more accurate description of the theoretical capability of the battery. So just a side note, it's important to know that from a technical standpoint. But let's summarize here. In this video, we've described various definitions of capacity and why measuring capacity is important for manufacturing as well as for consumers, right? Making sure that my phone isn't at 70% just after 70 days of running it. We've reviewed the process of approximating capacity through Coulomb counting, and we've gone through an example method using pandas. We've looked at the very first charge discharge and then going through an aging data set. Finally, with the observed differences between charge and discharge capacity, we ran an example script showing how that capacity varies over time, and we even calculated the coulombic efficiency of a battery. Now, I'll give you a challenge. This data set it can be posted, and you can find it on Kaggle from NASA. And you might be interested, if you want to take this a step further, and looking at how the capacity might change or vary from battery to battery. If you're interested and you want to do that on your own, great, go ahead. Otherwise, come see me in one of our other videos. We'll tag a link to it and you can check out how we would do that next. So thank you so much. I hope you've enjoyed this lecture and found it useful. As always, the code book will be posted on GitHub, and you can reach out with any questions. Thanks so much, and take care. Hey, thank you so much for watching this video. I really hope that you found it useful. If you want to look at more videos for battery data analysis or PyBEM and learning about some of its basic features, go ahead and subscribe to this channel. If you have questions, let me know in the comments. I'd love to see what content you would find useful. Thanks so much, and we'll see you soon.